Number 82, integrated concepts. Letter A. A 0.14 kilogram baseball pitch at 40 meters per second horizontally and perpendicular to the Earth's horizontal 5 times 10 to the minus 5th Tesla field has a 100 nanocoulomb charge on it. What distance is it deflected from its path after traveling 30 meters horizontally? All right, so first thing is we know that a certain charged particle will experience the Lorentz force and then will be curved, right? It will have its path curved in a magnetic field. So we're going to use this formula over here to figure out the radius of curvature, right, for that particular path. So this is kind of going to tell us, you know, the path that the ball will be traveling on. So it's the mass times the velocity divided by the charge times the magnetic field. The mass of the ball is 0.14. The velocity, they told us, is 40 meters per second. The charge on it is 100 nanocoulombs. Convert that into coulombs, so multiply it by 10 to the minus 9th. And then the the magnetic field is going to be 5 times 10 to the minus 5th. And let's calculate it, all right? So we're going to get 0.14 times 40, divided them by, parenthesis, 100 times 10 to the minus 9th, times 5 times 10 to the minus 5th. All right, so we get about 1.12 times 10 to the positive 12th. Okay, it's huge. Meters. That's the radius of curvature. What that means is this. Imagine you have the ball here, and it would travel if it were to be stuck in the Earth's magnetic field, basically would travel in this circular path, and everything is looking like an oval at this point. All right, that's a circle. Let's just line it up. Okay, so this is, by the way, not even close to being to scale, okay? But the radius of curvature of this path, all right, is going to be about 1.12 times 10 to the 12th meters. We're talking a tremendous, you know, it's a trillion meters, right? Now, what's happening here is that the ball is traveling horizontally, okay? At 40 meters per second. And it says it's going to travel, I guess, 30 meters horizontally. Now, there's going to be a lot of assumptions we're going to have to make in this problem. All right. Let's just say it's traveling 30 meters horizontally like that. Now, the thing is, though, the actual path of the ball here is outlined in blue. So really, you know, when the ball travels 30 meters horizontally, it's not going to be at this point. Rather, it's going to be at a point below that. Let's say, call it right here. Put a little dot there. Okay, let's call it that point. Let's move this around maybe a little bit. Okay, cool. And maybe let's get rid of this kind of circle at the top. We'll put in just a dot there. Okay. Now what I'm noticing, so this basically, now this distance here, right here, that I just drew, represents kind of that deflection, the y. Now, I start realizing I got some shapes I can kind of begin to start drawing here, right? I can kind of create this little triangle thingamajig, right? And we also know that, you know, the particular length on this side, it's also a radius, so it's the same as 1.12 times 10 to the 12th, right? Now, the assumptions we're going to make from here on forth is going to be this. This is a trillion meters, all right? So keep that in mind. Therefore, this horizontal distance, this radius of curvature here, or excuse me, this length of curvature, and this, we're just going to assume that they're literally all the same. They're all 30 meters. Because in reality, they're going to be like within 0.0001%. So we're going to just assume that they are all the same. All right, in reality, they're not, but to solve this problem, that's how we're going to do it. So what we're going to realize from this is that if I assume that this arc length here is 30 meters, okay, then what I can do is I can solve for this angle in there, okay, that angle. How? Well, through the formula that the arc length there will be equal to the radius multiplied by the angle. So the arc length here was going to be 30. The radius is going to be 1.12 times 10 to the 12th. Find the angle then, and what do we get here? So it's going to be 30 divided by 1.12 times 10 to the 12th. And it works out to be, that angle in there is 2.68 times 10 to the minus 11th. I mean, you can kind of already get a feel for, you know, how big this angle is. It's nothing, right? It's basically nothing. That's why we can make all these assumptions. Okay, now what I'm going to do here is, let me kind of clean this. Let me see if I can clean this up a little bit. 1 second. Okay, cool. So now what we have found is we have found this angle here. I'll call this maybe, let me do this in green or something. I don't know. Let's call this angle 1. All right, so this is angle 1 or theta 1. Now what I'm going to do is I got to start figuring some stuff out here in terms of the angles. We know this makes a right angle here because I'm assuming it starts right at the top. Okay. In other words, what that means is that the angle in here, let's call this, it doesn't really matter, theta 2. And let's call this in there theta 3. I know then that theta 2 plus theta 3 have to equal 90 degrees. Okay. What I also know is that, let's call this other unknown angle in here, let's call this theta 4. I know that that theta 4 then, or I could say that theta 4 plus theta 3 plus then that 90 degree angle up there on the top in here, right, has to equal 180 degrees because they all have to add up to 180 degrees inside that triangle. Notice how we can kind of simplify this a little bit and just have that then equal to 90. Okay. Now what's interesting about this is that I can now find a relationship between theta 2 and theta 4. You can do all types of substitutions if you want. All I'm going to do is I'm going to subtract these two equations from one another. And that tells me that theta 2 minus theta 4 is going to be equal to 0. In other words, theta 2 is equal to theta 4. Oh, that's interesting. Right, so what we just found is that this theta 2 right here is equal to this theta 4. They're equal. Okay. Interesting, right? So don't forget that inside of this triangle as well, inside of this red triangle, this is also a theta 2. And the reason why is because if this red side is equal in length to this red side, then their angles opposite of one another must also be equal. Okay, all this is like way, way back when in geometry, right? Okay, so I have that particular relationship, right? Theta 2 must equal then theta 4. So now consider that all these angles inside of that red triangle have to add up to 180 degrees, right? So this is theta 2 plus theta 2 plus theta 1 has to equal 180 degrees. In other words, 2 theta 2s plus theta 1 has to equal 180. Also, we know that that angle theta 3 and theta 4 have to add up to 90 degrees, right? Because there's a 90 degree angle in there. So in other words, we know that theta 3 plus theta 4 has to equal 90 degrees. Now here's the thing. If I divided this whole top equation by 2, right? In other words, if I did theta 2 plus 1/2 of theta 1 is going to equal 90 degrees. And I also know that theta 3 plus theta 4 is equal to 90 degrees. And since these both are equal to the same number, I can set them now equal to each other. Just like this, right? And now I can do some simplifications. Now I'm trying to relate my theta 1, because I know what that is, to one of the angles in here, like theta 3 or theta 4. So I realize that I want to get rid of this theta 2 on the left-hand side. I'm going to substitute it in with a theta 4 because I think I'll get some things canceling, right? So now what's going to happen is this is theta 4 plus then 1/2 theta 1 is equal to theta 3 plus theta 4. And notice, lo and behold, these theta 4s go bye-bye. And what I'm left with is that theta 1, or half of theta 1, is equivalent to theta 3. So half of this theta 1 is equivalent to theta 3, and almost that looks like the case in the picture, even though it's not fully to scale. Okay? So now finally what I did was I'm able to now relate this angle in here into an angle inside of this black triangle, and now I can finally calculate the y. Okay? So let's do this. Let's move this relationship on over just in case we need it. I don't think we will, but you never know. So let's erase some of this work now. And okay, and let's not erase that at the top. All right, so now to find y, if I know basically the measure of angle 3 now, because that's what we realized, I can now basically just do a tangent because I know that particular side in relation to the angle theta 3. So we can say that the tan of theta 3 now is equal to the opposite side of y divided by then the adjacent side of 30. So the tan now of angle 3, but angle 3, remember, was half of theta 1. So I'm going to do that substitution. And then now I'm going to plug in the value of theta 1 because we found it. It was 2.68 times 10 to the minus 11th. It's up there on the top right. And that's going to be equal to y over 30. Now, when you do this, please be careful. Make sure your calculator is in radian mode. Otherwise, it's not going to come out right because theta 1 is technically in radians. Okay? So, all right. So now we need to do tangent. All right, of 0.5 times then that exact value. Let me go back in the calculator and grab it. Okay, close those parentheses, multiply it by 30, and voila. So we get about 4.01 times 10 to the minus 10th, and that is now in terms of meters. All right, remember it is an approximation, but we're definitely not going to be far off. All right, and then it says, you know, would you suggest this as a secret technique? No. Guys, thanks for tuning in. Appreciate it. Please help us out if you can and subscribe. Really appreciate it very much, and I look forward to helping you with more problems. Take care.